Thank you. Thanks for coming back for the second and last part of groups acting on trees. So the two parts will not be of the two topics that I wanted to talk about will not be of the same length. So I'm going to finish talking about what I started last time. So I've written a little reminder. So we care about automorphisms of a D regular rooted tree where D is at least 2. And I wrote last time that we can think of an automorphism of such a tree. So here's a part of the binary tree. We can think of it as defined by what's called its portrait. So what does that mean? It means that at each vertex of the tree, I write a permutation of the vertices that lie below that vertex. Okay, so here I can either swap these two or not. Here I can swap these two or not, etc., etc. Okay, and we'll say that a group of automorphisms of such a rooted tree is self-similar if it is invariant under the right action of the free monoid D star. So all the vertices of the tree, if it is invariant under the action of the tree on the group. What was this action? Well, suppose that here is my element G. It's got its portrait. Okay. Then I can look at what is its shift by, say, the letter 1, the symbol 1. Well, it's just looking at this subtree that starts with the symbol 1 and pretending that this is the whole binary tree. Right? That's it. And I want this configuration to be in my group. So, and I want this to be true, not just for the letter 1, but for every other vertex of the tree. Okay, so that's what it meant to be self-similar. And I need to recall some notation or definition, which is that a pattern of size n is one of these portraits, but it finishes at some finite level. So a pattern of size n is an element of sim d to the n. So here is a pattern of size, how much? Just in case we agree. D, sim d to the 0, sim d to the d, sim d to the d. So that should be a pattern of size n plus 1, right? So I didn't agree with my own notation. Great. It doesn't really matter. I just want them to be, these things will, the only thing that I will care about is the fact that they are finite. Okay, and I made a remark last time saying that, well, what is the topology? Here, this comes with a natural topology, right? So a finite set has a discrete topology. I'm basically taking the product of a bunch of finite sets. I put the product topology on all of that. Tikhonov tells me that this is compact. Great. Okay, so I have a nice compact space. It turns out that and these two things are they're essentially the same set. They're the same set. It's just that the group operation is not a direct product, right? I don't compose things coordinate by coordinate because there will be some twisting in the tree. So let's do a little exercise to check that this topology is actually a group topology. So the composition and inversion are continuous operations. Okay, so I'm just going to do composition, and I'll leave it as an exercise to do inversion, because if you've understood composition, then you can understand inversion. Okay, so let's say I've got two automorphisms of my rooted tree. So that's two configurations, two infinite portraits that are the limits as n tends to infinity of a bunch of automorphisms. Okay, so what does it mean? What does it mean that f is the limit of all the fn's? Well, it means that no matter how deep I want to go, so that's an open, right? The opens are things that do something up to a finite level. I will be able to find a sequence. I will be able to find a point in my sequence of fn's such that from that step on, all fn's do the exact same thing as f here. They have the same pattern up at the top. Okay, and the same thing for the g's. Okay, so that's what it means for f to be the limit of the fn's, and the same for g. Now what we want to show is that So we want to show that F composed with G is the same as the limit of Fn composed with Gn as n tends to infinity. Okay, so now we need to remember how to compose these things, right? The multiplication is not just doing it coordinate by coordinate, otherwise it would be a very boring group. So let's check. So suppose I have my alpha. I'm going to write it in this form. Alpha does some permutation sigma at the top, and then it will do some alpha 0, alpha 1. I don't know what they are. I mean, I don't know. It's stuff. Okay, some things. And I write it like this: alpha 0, alpha 1. And I suppose I have beta, which is some tau, and then it does beta 0, beta 1. So that's the same picture. Here's tau, beta at 0, beta 1, and there's some other stuff happening here. I don't know what it is. Okay, how do I compose these things? The composition of these two things is, well, I built the notation in such a way that, okay, so this is sigma alpha 0, alpha 1, tau, beta 0, beta 1. And I've built the notation in such a way that, okay, so I have to put the tau over to the left. And I've built it in such a way, you can check for yourself, see what happens to a word, see what happens to a word that starts with 0 when you do both of these things. I've done it in such a way that what will appear here, I'm going to give myself some more room. What will appear here is sigma tau alpha, well, no longer of 0, but of wherever tau takes 0. Watch out, this is not the standard wreath product notation. Sometimes you have to do tau inverse of 0, but it's just because I've chosen the wreath product I've chosen to write the wreath product in this way so that I can write it like that. If you choose the other wreath product notation, you will probably end up with tau inverse. Okay, but right, so what I get at the top is sigma tau, and then, okay, I have to compose either alpha 0 with beta 0 or alpha 1 with beta 1. This is why it's not just a straight direct product. Right, so we want to show that the limit of these two things is, sorry, that the composition of these two things is the limit of all of these compositions. Well, if I compose a bunch of these Fn and Gn, okay, I'm just doing this, right? There's this composition, and I know that Fn and Gn each tend to F and G, respectively. So up to some level, if I look at a finite portrait up to some depth, well, what's happening here? I'm composing Fn and Gn, or I compose F and G, and I know that if Fn and Gn are in a deep enough, or in a large enough open, small enough open, so deep enough in the tree, then actually the portrait that will appear here will be the same as if I compose F and G. I'm not sure if I've made myself clear. Right, up to a certain level, this composition is exactly, I mean, it's a finite thing, so we don't really care what happens below. Yeah. Correct. If I know Fn and Gn up to level n, then I know the composition up to level n. Yes. That's a better way of putting it. Thank you. And so this should convince you that this equality is indeed true. Yeah. Okay. Great. So exercise, do inversion. It's essentially the same. Okie doke. So I wanted to do this thing slowly because I want people to get used to topological groups. Maybe everybody's an expert in topological groups here. I don't know. But when I was a younger researcher, I found topological groups very scary. So it's good to get your hands dirty and do the exercise and see that it's not that scary. Right, and so this is a topological group, so it means that So this means that isom D star is a topological group. It's compact. Well, okay, I'll talk about that later. So it's enough. So for a topological group, if I know that the topology on my group is such that composition and inversion are continuous, then in order to define the topology, it's enough to know what are the neighborhoods of the identity, because I will translate the identity to every other point, right? So it's enough. So it's defined by the neighborhoods, how do you abbreviate neighborhoods of the identity? And what are the neighborhoods of the identity? Well, what are the neighborhoods of the identity? Well, the identity is the thing with the completely empty or trivial portrait. So they are the things that don't do anything up to level n. So these are what I called the nth level stabilizers. Right, this is important. Okay, so that means that every open in isom D star is a union of cosets of STNs, level stabilizers. Right. Okay, do I want to say anything else? No, that's it. I think this is all I wanted to recall. Questions? No, one last comment. It's a compact, totally disconnected group. Right, it's compact because of Tikhonov's theorem, and it's totally disconnected because these things, because we said that these things are the basic neighborhoods of the identity, but in fact they're also closed, right? Because they are the complement of a union of cosets, right? Cosets are supposed to be open, and so I take all the cosets that aren't the trivial one, that's an open thing, and the complement is this one, so it's closed. Okay, so my topology has is defined by basic clopens, and so that means that it's totally disconnected. And a compact, totally disconnected group is called a profinite group. Called a profinite group because it turns out to be an inverse limit of finite groups, but I am avoiding all of that completely. So if you're scared of limits, either direct or inverse, then don't worry. Okay, right. Now I can go back to the last theorem that I wrote on the board yesterday. Here it is. And it's a combined theorem. So part of it is a result of Grigorchuk, and the other part is a result of Sunich, and you can read I think you can read the whole proof in Sunich's paper from 2006. So it says, if I have some S at least one, then the following three things are equivalent. The first one is that my group of rooted tree automorphisms is a finitely constrained group. So being finitely constrained means that it's a closed self-similar group. So that means that it's a tree shift, and that means that it is defined by forbidding some patterns of depth, whatever. And being finitely constrained means that it's enough to define finitely many forbidden patterns. Okay, so it's enough to forbid finitely many patterns, and I might as well assume that they're all of the same size S. Okay, so that's the size. This is equivalent to my G being a closed subgroup of the automorphism group of the tree. It's self-similar. Okay, so far this just says that it's a tree shift. So now what we're translating is, what does it mean to be defined by finitely many forbidden patterns? Being defined by finitely forbidden patterns is equivalent to satisfying this condition B, which says that, okay, so long as we have a group, which says that if I choose D many elements that stabilize level S minus one, so here's a picture. D is 2. I have an element here. It stabilizes level say 2. It doesn't do anything here. It doesn't do, oh, sorry, that way. It doesn't do anything there. Okay. And I have another one like that. And now I can build a new automorphism of the tree, which is just do G1 here, do G2 there. Don't do anything at the root. That's a perfectly valid tree automorphism. Do we all agree? I mean, it's just do this tree automorphism, do this tree automorphism. Don't do anything at the root. There's no reason why that should, and do we agree that if G1 and G2 don't do anything up to level 2, then this new element won't do anything up to level 3? Yeah, because we've added an extra level. Okay, so we agreed that this new element is in the stabilizer of level S, but there's no reason it should be in G. There's no reason it should be in my group G. So the condition is that this is actually in G. Okay. 1 and 2 are equivalent. So this is for a closed, so for a profinite subgroup of tree automorphisms. This is equivalent to G being the closure in isom D of a countable self-similar subgroup that satisfies the same condition. Right, so let me give you some examples. The most trivial example is if G is the whole automorphism group of the tree, and we can take as C as the countable self-similar subgroup that satisfies condition B, we can take the finite tree automorphisms, which is, if you remember, it's those ones such that from some level on, the portrait is trivial. We just do the identity. Okay, so this is defined, we said the other day, is defined by forbidding patterns. Which patterns? Of size what? Well, let's do it another way. What am I allowed to put on each of the vertices? Everything. I can put everything. I can put the whole symmetric group on all of the vertices. So it's defined by not forbidding any patterns or by allowing all patterns of size 1. So it's defined by patterns of size 1. So that's just the whole of the symmetric group there. And what does this satisfy? Well, we said it the other day that G can be written as what? It can be written as the symmetric group acting on the root, and then there are D copies, right, hanging from each of the vertices of G itself. Right, I can put whatever I want. I mean, this is you all agree with me before that I can put whatever automorphism I want here, whatever automorphism I want there, and in fact, whatever I want at the root, and that will still be a perfectly valid automorphism of the tree. Okay, so you all agreed with me before. So this is sim D wreath G, and in fact, C also satisfies this thing. Because if you stop doing something up to some level, then this is preserved. Okay, so right, it's important that being defined by patterns of size 1 means that there are, I can put D copies of my G at level 1. It's an important thing to notice. I can also make a less trivial example, but still pretty easy. Pick F to the D star for F any subgroup of the symmetric group. So I can take the alternating group, I can take a cyclic group, like anything, any group of permutations. Okay, so this is now also defined by patterns of size 1, right? Because I can put at every vertex any permutation from F, or if you want, I have to forbid the permutations that are not in F. Okay, so this is also defined by patterns of size 1, and I can define a CFD star finite tree. So also defined by patterns of size 1. Of size 1, and G is also isomorphic to, well, it's now no longer sim D, it's now F wreath G, and C is, well, I'll write isomorphism because okie doke. So far easy examples, right? I just want you to notice that there are D copies of the group acting on stabilizing the first level and then doing whatever they want independently on the trees below. That's the thing that you want to notice. Right. Now suppose, so for gamma, any of the examples above, you have the following thing. I'm going to define wrist gamma of the vertex 0. This is by definition the elements of gamma whose support is entirely contained in the subtree that begins with 0. So here's 0, here's 1. It's all the guys that do something to that subtree and leave everything else fixed. Right? That's the rigid stabilizer of vertex 0. Do you agree with me? No pressure. No pressure in agreeing with me. That this, okay, so what stuff for our examples, what elements act only on the subtree rooted at 0 and leave everything else fixed? What am I allowed to put here? Is there anything that I'm not allowed to put? Nothing, right? I mean, I can put gamma again here. So these are all the gammas of the form do nothing at the root and then do G0, so long as you do the identity everywhere else. And this is for G0 in gamma. So let me write this as identity semi-direct gamma times identity. Now, so the same way that I define wrist of 0, I can define it for any other letter of my alphabet. And now wrist gamma 1, this is why I use the underlining for the symbols, is the subgroup generated by wrist I for I in D. So that's the product of all, well, the subgroup generated by the rigid stabilizers of all vertices at level 1. Okay, so I said product. The thing to notice is that if you only act here, so if I have an element in the rigid stabilizer of 0 and I have an element in the rigid stabilizer of 1, their supports are disjoint, so they commute. So this is actually a direct product. And what is this for these examples? Well, I mean, we've seen what it is for 0, and nothing changes for the other ones. So it's the wrist I is gamma in the ith position. So this is simply the identity semi-direct gamma to the D. Well, what subgroup is that of gamma? Yeah, exactly. It's the stabilizer of level 1, which we said was a basic open or a finite index if we're only dealing with the if we're only dealing with the discrete case. So this is a finite index in gamma. Also, a fact about these groups is that this is a closed subgroup. So a closed subgroup of finite index is open exercise. So if I'm in a topological group, a closed subgroup of finite, well, definitely in a finite group, a closed subgroup of finite index is immediately open. Okay, so this is going to be important. The fact that RIST1 is of finite index or open in gamma. Let me do some more examples. So still examples. Example C. So if G is the Gregorchuk group, then what we have, and this is because somebody calculated it, I don't expect you to do it. It's not an exercise. Or maybe the exercise is to find it in a book or something. We have that. So using the same notation, the stabilizer of level 4 contains 2 copies of the stabilizer of level 3. Right? In the same way that we had in the picture. I can put whatever I want in the stabilizer of level 3 on the left tree. I can put whatever I want, the same thing on the right subtree, and that will again be an element in curly G. And for GP, the Gupta-Sidky P group, this is a uniform thing in all primes. The stabilizer of level 3 contains the stabilizer of level 2, well, on all of the levels. Okay, so that's condition B, right? They satisfy condition B less trivially than the examples that we had before. So let's see what happens. So from condition B being satisfied for S equals 1, we got that RIST1 is the stabilizer of level 1. Now let's see what happens if we satisfy condition B for a larger S, which is what happens in these 2 examples. Let's see what happens. So suppose that we have STGS contains STGS minus 1 to the D. So that's what condition B tells us in different writing. If we have this containment, well, okay, my group G is self-similar. I'm gonna need the picture again. My group G is self-similar. So if I have something that stabilizes level S, and I look at its sections, they have to be again in G. And of course, they stabilize level S minus 1. So what this is saying is that I always have the containment the other way if my group is self-similar, right? So the important thing of the theorem is that we have equality. The importance of condition B is that we have equality. Okay, so this now implies that RISC G of the first level definitely contains all of that, which is exactly the stabilizer of level S. Okay, so now we've got RISC1 contains stabilizer of level S. We still have that this is something of finite index or a basic open. Similarly, what happens now for RISC G2? I want to know what happens for every RISC N. What happens for RISC G2? Well, let's draw a picture. So for RISC2, this is the guys that do whatever they like on these subtrees. Yeah, okay. But what I can use is that I know that if I put here something in STG S minus 1, whatever I want in any of these 2 coordinates, then condition B tells me that this whole thing will be in STG S. And the same thing here, STG S. But of course, STGS, if I stabilize level S, then I also stabilize level S minus 1. Aha, so now I've got two elements, one that stabilizes level S minus 1 and another one. So condition B again tells me that all of this is in the stabilizer, is in G. The point is that this is in G. So this is telling me that risk G2 contains D squared copies of ST, of the stabilizer of S minus 1. Right, I've got 1, 2, 3, 4 copies of the stabilizer of level S minus 1. So this contains, right, the identity STG S minus 1 to the D squared. And this also, by the same logic as before, is the stabilizer of level S plus 1. So if you agreed with me up to here, then you will agree with me that the rigid stabilizer of level N contains the stabilizer of level S plus N minus 1. Okay, so which is, of course, of finite index in G, or open, right? I'll just say finite index because these things are all closed. All right, so this is saying that all these rigid stabilizer things are a finite index. Okay, and this, remember, this is what happens if you are finitely constrained. If you are finitely constrained, then you satisfy that all these rigid stabilizers of levels are things of finite index or open. But what happens for if G is the odometer or the infinite dihedral group? What is the rigid stabilizer? What is the rigid, let's say, what is the rigid stabilizer of vertex 0 for the action of the odometer? Well, if it were non-trivial, then I would be able to conjugate it to the rigid stabilizer of vertex 1 because the odometer takes this subtree to this subtree. But conjugating in an abelian group doesn't do anything, so it must be trivial. And similarly for the infinite dihedral group. So basically, this is the argument for saying that the odometer acts, what was the word? Freely. No. Or essentially freely, topologically free. I can't remember what it was. You can't have this independence. And similarly, we had PSL2Z, which is the free product of C2 and C3. Well, a free product or something which is virtually a free group does not have, what is this? This is a huge direct product. And huge direct products do not live in virtually free groups. So this is does not have finite index subgroups that are direct products. All right, so that tells me like that none of these actions, if I take the closure of the odometer, if I take the closure of the self-similar action of the dihedral group that I showed you, if I take the closure of the self-similar action of this group, none of these are finitely constrained. They're defined by infinitely many forbidden patterns. Which ones? I don't know. What kind of complexity? They're defined, I mean, they're a what kind of tree shift in terms of complexity, one of these words, suffix, or I don't know what. So that there's a question for people in symbolic dynamics, figure out what the complexity of these things is. Right, what else? I think I need this board. Okay. Yes, I'm gonna switch. So groups, the examples of groups satisfying B are what's called branch groups. So I'm going to define a branch group. So what's a branch group? So I'm going to start out by now changing notation. So MN is going to be a sequence of natural numbers at least 2. And I'm going to define T sub MN to be the rooted tree, which has, so at the root has M1, children. The vertices of level 1 have M2 children, all of them. They've all agreed for some reason that they're going to have the same number of children. It's some strange population experiment. Vertices at distance 3 all have vertices at distance 2 have M3 children, and so on and so on. So it's a level homogeneous rooted tree. All vertices at the same level have the same valency, the same number of children. And of course we can consider, I'm still going to call it isometries because automorphisms will appear later. So we can of course consider the group of isometries of this tree. So a subgroup of this group of isometries is a branch group if it satisfies 2 conditions. The first one is that it is transitive on all levels, at every level. And the second one is that for all n, the rigid stabilizer of level n has finite index in G. So of course G can be closed. G can be closed or no. I can just consider it as a group, or I can consider it as a closed subgroup. Right, and if this happens in the case that G is compact, that G is profinite, then these things will be basic opens. These things will define the topology for me. I'm making this comment because it will be important later. Why do we care about branch groups? Well, okay, examples, I already said it, right? All the examples that satisfy this condition B are branch groups, but of course, they were all self-similar. So now this is a wider thing because branch groups don't need to be self-similar. They just need to satisfy, that they have enough transitivity, so they act minimally on the boundary of the tree, if you prefer that language, and the basic opens decomposes direct products. Why do we care about branch groups? Well, we care because first of all, because of the examples. They contain all of these examples with exotic properties, Burnside groups, and so on. They also contain interesting iterated monodromy groups. We also care because of what I'm about to tell you when I finally start the second part. And we also care because of a sort of taxonomy. I don't want to call it a classification. I was told I should call it a taxonomy of just infinite groups. And this is due to J.S. Wilson in the 70s, which says that if G is a just infinite group, bless you. So that means that it's infinite, but it's only just managed to be infinite, but all proper quotients are finite. So examples of just infinite groups, the integers. right? They're infinite, but all quotients are finite cyclic. The infinite dihedral group is another example of a just infinite group. I'm going to hit you with a big theorem. PSLNZ is just infinite because of a big theorem by Margulis. And all of these examples, the Grigorchuk group, the Gupta-Sidki group, these finitely constrained groups, right? The examples where I gave that were constrained by patterns of size 1, these are just infinite groups. So John Wilson's taxonomy says that if my group is just infinite, then either G is virtually H to the, I don't know, H to the some K. There are K, it's a direct product of a finite number of copies of some H, where H might be simple or abelian, or Z, basically. Simple, Z, or something like PSLNZ for n at least 3. Or G is a just infinite branch group. So what are just infinite groups good for? Well, every finally generated group, which is infinite, has a just infinite quotient. So if you want to study properties that pass to quotients, they're like they're sort of the atoms. They're not quite the simple groups because they contain simple groups. They contain a little bit more, but it's sort of the minimal unit that you should be studying. Okay, so I'm arguing that branch groups are an important class of groups for all of these reasons. Questions? No? Okay. Right, so let's go on to part 2. So part 2, groups acting on unrooted trees and beyond. Okay, so now D is going to be the D+1 regular unrooted tree. So here's a picture for D is 2. Okay, and it goes off in all directions. And now I'm finally going to use ought to denote its automorphisms. Graph isos from T to T. So this group, this is a locally compact group. In other words, I can put a topology on it, which is locally compact. So every point has a compact neighborhood. And this is a group topology, meaning composition and inversion are continuous. And why can I put this topology? Well, it's a locally compact group because it commensurates. So I'm going to repeat what Hannah defined the other day because it commensurates. What notation did I choose to use? It commensurates the stabilizer of, I'm going to choose once and for all some vertex V in my tree. It doesn't matter which one it is, just choose it. And this is going to act as my origin. So if you want, you can think of the tree as being like the affine plane And I'm just choosing an origin. So what is this? I have chosen this origin. And if I look at everything from the point of view of this origin, well, there are 3 edges coming out. And out of each of those 3 edges, there are 2 edges coming out. Aha, so this is the isometric group of the tree of type D plus 1, D, 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 D. So it's one of these branch groups. What does it mean? What does it mean to commensurate? What does it mean to commensurate? It means, i.e., for every automorphism of T, I'm going to give a slightly different definition to the one that Hannah gave, but this is good because then you see both points of view. What we have is that for every G in OT and for every U open subgroup of isom T, I'm just going to call this thing I, because I'm going to get tired of writing it. So for every open subgroup of this stabilizer of a vertex, we have that that there exists some V open in I such that G, U, G. So if I conjugate an open of my I, that contains some other open. So the intersection, i.e., the intersection of the conjugate of U and U is open in both. Right. Okay, that's just the definition of commensurating. What's it good for? What's this have to do with the topology? So there's a lemma. There's a lemma which I'm going to call lifting topology from subgroup. There's a lemma. I mean, it's like in Bourbaki or something like that. There's a whole chapter on topological groups, and it's right at the beginning. We define a filter. There's a filter and a filter base, and this is what a filter base of neighborhoods has to satisfy in order to be a group topology. It's done in all this huge generality, but I've extracted it to just apply to this case. And it says if curly N is a filter base of neighborhoods, sorry, not of neighborhoods, of consisting of subgroups of G. So what does this mean? So a filter base is just a collection, in this case, of subgroups, such that the intersection is contained again in the collection. The intersection of any 2 subgroups is again contained in the collection. Filter base means that if we take things that contain anything in N, that will be in our filter. Right, so we will take the filter generated by all of this. Such that for every G in G and for every U in my filter base, there exists some V in my filter base, which is contained in the conjugate of U. Then if blah, 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 then N is a filter base of neighborhoods of the identity for a unique group topology on G. So what's the idea? The idea is that we're going to take, the idea is what? The idea is that we're going to take the things that are open in I, the open subgroups of I, That's a filter. That's a filter base, right? Because if I intersect two opens in I, they're still open in I. Fine. G is going to be odd T. So my filter base N is all the opens in I, and G is odd T. And if they satisfy this thing, which is exactly what I wrote there, then it turns out that all the opens in I are a filter base of neighborhoods of the identity for a topology on odd T, which means that all the opens in odd T, well, the neighborhoods of the identity in odd T are just subgroups of odd T that contain an open in I. That's what this means. And therefore, all the opens in odd T are just cosets. They're cosets of subgroups that contain an open in I. And this is how you generate a topology for odd T. Right. And shall we see why this holds and then have a break, or shall we have a break now because I've gone on for a long time, and then see a proof? Yes, break. Okay, let's have a break then. 10 past 12. Okay. 12 past 12. Very good. Very symmetric. I like that. Okay, thanks for coming back at exactly 12:12. So let's continue. I said right. So what do we have to do? Little exercise. So we're trying to understand why the automorphism group of a D+1 regular tree is a topological group. We're trying to find a nice topology on it. Actually, okay, I could have cheated and told you what the topology is, but I want to do this exercise because I'm going to use it later. So how do I get a topology? How do I get a nice topology to put on odd T? Well, I get it from a subgroup where I already know a topology, and the subgroup is I, so the stabilizer of this vertex, so the isometries of this rooted tree. And we're saying that what I need to do is show that the automorphism group of the tree commensurates this I, this subgroup I of isometries. Because there is some lemma in like general topological groups that says that this is all I need to do. I did think I could prove it in a short amount of time, but I don't think I can do that because I'm supposed to finish when? 10 to, yeah, I definitely don't have time. So, okay, if I do have time at the end, then you can ask me questions or maybe we can talk during the break if you're really interested in this. But let's do the exercise of showing why odd T commensurates I. So odd T commensurates I, so the stabilizer of a vertex. It commensurates I because what? Because, well, let's see. I have to show this is also equivalent. Okay, so I need to look at let's see. I have my G, my automorphism of the tree. It will take my origin V, I don't know where, somewhere, not too far away in my picture, so that I can draw it. It will take it here, all right? So if I translate everything to my rooted picture, that's V here, and I'm going to draw it in such a way that 1, 2, 3. I'm going to draw it in such a way that GV is there. Okay, so GI inverse contains of course the intersection of G inverse and I. So what is that? What is the if I stabilize this and I also stabilize that, then that's of course the stabilizer of that path. And if you want, right, I'm considering it inside I, so I'm considering the automorphisms of this rooted tree that fix this vertex. That's of course an open. But That's it. And similarly, the other way around, because if I draw the picture the other way around, then it's the automorphisms of this rooted tree that stabilize this other vertex. So that's of course open. So that's easy. So that's just the stabilizer in I of vertex GV, which is open in I. Yeah, and that's all I need to show, right? I need to show that this thing contains some basic open. So we could have done it before the break, but you wanted to break, so that's good. And this means that this is now completely easy and not confusing because you were tired. Right, so this now means that OT is a locally compact group. Because I is open, right? In this new topology, I is of course one of these basic opens because I is open in itself. And we said that the topology of OT is take the basic open subgroups are all the things that were open in I, or things that contain subgroups that contain an open in I. So I in particular is open and is compact. Right, so I've got a compact neighborhood of the identity. So my group is locally compact, and it's totally disconnected. It's totally disconnected, which I'm going to abbreviate to TD, and this I'm going to abbreviate to LC. So it's TD-LC. It's totally disconnected again because my basic opens are subgroups, and therefore they are also closed because they're the complements of cosets. Okay, so my group is TD-LC, and what else? It's a TD-LC group. That's great. It's also generated by I, the stabilizer of this vertex, and I'm going to call them, I don't know, elements E1 up to ED, where these things are, they can be whatever you like, actually. You can think of this as an edge inversion. You can think of them as edge inversions to the D neighbors of V, or they can be translations. They can be anything that takes V to one of its neighbors. That's enough. So all of that is enough to generate the whole automorphism group of the tree. I is compact, and I've only added finitely many things. So this whole thing is compact. I know that I haven't actually explained why this thing generates. But it's basically, I mean, okay, I don't have the time, but it's not too difficult to do. And I don't want to be cheeky and say exercise, but you can also look it up. It's not very hard. Okay, so it's a compactly generated TD-LC group, and of course it's non-discrete. It's not discrete, right? The topology is not discrete, so that's it. And what else? The important thing is that Jacques Dietz proved in 1970 that OT plus T, so this is the subgroup generated by all edge stabilizers, which is the same as orientation preserving automorphisms, that this thing is simple, meaning on the nose simple, no normal subgroups, whether open or closed or dense or anything, no topology involved. It's simple as a group. And this is, of course, this subgroup has index 2 in OT. Okay, so I have a subgroup of finite index inside a TD-LC group that is compactly generated. This thing is going to be a TDLC group that is compactly generated as well. Okay, so odd plus T rather, is an element of the class, is in the class curly S of TDLC groups that are not discrete, compactly generated, and topologically simple. And now topologically simple means no closed normal subgroups. No non-trivial, etc. No non-trivial. Of course, being simple implies being topologically simple. Okay. And the proof of, I can definitely not show you the proof of this in the time that I have, but that's okay. Right. So I've introduced this class. This is an important class, so I'm going to highlight it. And now there's less mathematics and more storytelling. Why do we care about S? Why do we care about this class S? Well, okay. I assume that in this school, people care about locally compact groups because they have a Haar measure, and so we can do analysis. Yay! We can. Excellent. We can do measure theory. So there's measure theory. We can do analysis. We can do harmonic analysis, Fourier series, all of that stuff. Fantastic. Okay, so we want to know, where can we do analysis? Where can we do analysis? On what groups can we do analysis? So what are the locally compact groups is the question. If I just give you a locally compact group, or you find one in the forest, what can you say about it? Okay, well, if I give you just some locally compact group that you find in the forest, then you can look at the connected component of the identity. That will be a normal subgroup. And of course, the quotient will be totally disconnected. Okay, so that's the first decomposition part. That's great. What do we know about the connected groups? Well, we know, thanks to the work of lots and lots of people, but I think I really need to mention Gleason, Yamabe, Montgomery, and Zippin, who did work in the 1950s, that connected locally compact groups are essentially Lie groups. They're projective limits of Lie groups. And if you're scared of projective limits, just think basically Lie groups. So things like GLNR and that SLNR and that kind of thing. So I'm going to say this is done, because I mean, it's not done. Of course, there's a lot of things to do still for Lie groups, but this is a very mature theory. So we know a lot about Lie groups. What do we know about TDLC groups? Nowhere near as much. Nowhere near as much. This is definitely not a mature area. So we know that at least, so for Lie groups, right, you can restrict to the simple, you can restrict yourself to considering the simple case. And the decomposition theorem that says an analogous thing for the TDLC case was proved in 2011 by Capras and Monod. I don't actually want to state the theorem because it's actually quite complicated. I just want to say that there's a theorem that justifies that if you have a TDLC group, then it's either hopeless because it's essentially compact or it's essentially discrete. And of course, discrete groups, right? Discrete groups are TDLC, right? If a point is open, that's definitely compact, right? And it's totally disconnected because the identity is open and closed. Okay, so we're definitely not going to classify all discrete groups. We won't be able to say anything about all discrete groups. Okay, so these are the cases where everything is hopeless, and we leave it to other people and we say, well, I don't know, I have to write papers. So I'm going to focus on some place where I can actually say something, which is this class S. So basically there is some decomposition theorem that says that, okay, you can except outside of hopeless cases, reduce yourself to studying these classes of simple groups. Right, and now the question is, can we classify groups in S? Well, there's a theorem of Simon Smith from 2017 that says that there are continuum many isomorphism classes of groups in S. Oh dear, horror. I mean, it's going to be very difficult to classify all of these up to isomorphism then. So but we don't lose hope. Well, we still go by analogy with Lie groups because it's very informative. So in Lie groups, you can study them via their Lie algebras, which is essentially their the local structure. What happens around the identity? What happens in a neighborhood of the identity? Okay, so now we don't have Lie algebras in this setting, but we do have, unless it's a p-adic Lie group, but okay, don't want to get into that. But we do have in all cases is open subgroups. So we study the open subgroups. So the question is, can we classify these groups in S up to local isomorphism? That is, can we classify them? Okay, so two such groups are locally isomorphic if they have isomorphic open subgroups. So around some neighborhood of the identity, they're the same. They might be completely different elsewhere. So for instance, just to give you a silly example, the isometries of a tree and the whole automorphism group of the tree are locally isomorphic because, of course, the first is open in the second, but they're very different groups. Okay, but around the identity, they do the same thing. And why is this good? Because all of Smith's groups are actually locally isomorphic to each other. Okay, so it's only one local isomorphism class that's given us continuum many isomorphism classes. So okay, so that's the idea or the hope that we should study what happens. Yeah. Exactly. So no, that's true. But I'm focusing on simple. I'm focusing on the simple case. Yeah. So if we just focus on simple, then at least for Lie groups, yeah. Yeah, of course. Nilpotent, I mean, also soluble groups are, yeah, already nilpotent is huge and soluble gets even worse. But if you focus just on simple, then it's okay. And in this case, it's not okay. That's all I wanted to say. Yeah, but thank you for the comment. Okay. Right. So no. What did I want to say now? Okay. So here's an observation. Suppose G is locally isomorphic to a group that we care about, say OT, for instance. Then that means that there exist open subgroups U1 and U2. U1 is open in G, U2 is open in OT that are isomorphic. And so if this is open in OT, then I can actually intersect it with I to get something open in I. And of course, this will be isomorphic to, I don't know, U1 prime. And this is also open in U2 and this is open in U1, right? Because I is open. I'm just intersecting two opens. This is still open. Right. So this says that if I want to understand, say, OT up to local isomorphism, I just need to understand the opens of I. I just need to understand what things are isomorphic to an open subgroup in I. And okay, so this means that we need to understand. So we need to understand. This justifies reducing to understanding the abstract commensurator, in this case of I. So this is the group of all isomorphisms between open subgroups of I up to some equivalence relation. And the equivalence relation is that two such isomorphisms are equivalent if there exist U3 open in I such that phi and psi are the same when restricted to an open. Right, so I'm looking at, okay, so okay. Right, so this might be phi, this might be psi, but if they do the exact same thing to this big open, then I'm going to consider them the same because I only care about what happens locally. Okay, so that's the commensurator, the abstract commensurator of yes. So open, you can think finite index. Yes, this is why it's the commensurate. Yeah, I'm using the fact that I is compact. Yes, but it's really finite index, and therefore it's the same concept that we had before about commensuration. Thank you for the comment. So this is finite index. I mean, if this were a group without a topology, then it would just be subgroups of finite index. Okay. So I'm saying that we want to study the abstract commensurator of the group of isometries of this tree. Okay, how do we do that? Exercise. This is a group. Is a group. Thank you for pointing that out. I just I just knew it and took it for granted. Yes. Of course it's a group. Otherwise I wouldn't talk about it. Okay, and there's a result by Lavrenyuk and Nekrashevich that says, I forgot the year, it's the early 2000s, that says that that implies since I is a branch group that the abstract commensurator of I is isomorphic to the relative commensurator of I inside the homeomorphism group of the boundary of the tree, which is of course a Cantor space. And now I have to tell you what the relative commensurator is. Well, it's exactly what you think it is. Homeo Cantor of I is all the H's in homeo of the Cantor space such that H inverse intersect I is open or has finite index, depending on how you want to look at it, in both the conjugate and I. Okay, so this is nice because I don't need to do this abstract construction and try to find all possible finite index subgroups and all possible isomorphisms between them. I can just look at a concrete action on the Cantor space. Okay, that's great. And now I'm going to throw a fact at you. And what's the idea for the proof of this? Well, the point is that the branch group, I mean, this is true for any branch group. The point is that the branch group knows that you can reconstruct the homeomorphism. You can reconstruct the Cantor space from the subgroup structure of the group, and therefore anything that you do here can be seen as a homeomorphism of the Cantor space. Where do I want to write? I'll write it here. So I'm going to throw a fact at you, and I'm only going to give you an idea of the proof. The fact is that the commensurator in homeo of the Cantor space of I is the set of all homeomorphisms of the Cantor space such that there exists some partition. So this is a Clopen partition. And there exists G1 up to Gn in OT. This is important. Such that H restricted to Pi is Gi restricted to, I'm going to call them alphas. Sorry, I wrote that in my notes, and otherwise I'm going to keep making silly mistakes. So alpha for automorphism. Okay, what is this thing? Let me draw a picture. Maybe I'll draw it on the other half. So let me give you an example of one of these things. Okay, maybe I'll draw it here. Okay, so here's my origin. Here's my origin V. And I'm going to make the following partition. So here is P1, all colors. Here is P1 is the boundary of this subtree. Yeah. P2 is going to be, what have I decided is P2? P2 is here. This is P2, P3, and P4. Okay, so it's basically the boundary of each of the 4 subtrees hanging off of this tree here. Okay, and I'm going to do some H, which is what? What is this H? So H is going to be on P1 and P, what did I write? And P3, what color is that? I do a rotation. Let's see, what rotation do I want to do? So maybe I'll do this rotation here and P, and that can be that rotation there. So let me draw the picture again. Okay, so this means that P1, here's my origin V. So P1 will be taken to here. No, is that will be taken, where is it? It's 1, 2 away from V. So that's 1, 2 away from V. Okay, so P1 will be taken here. So this is alpha 1 of P1. And P3 will be taken 1 away from V. So that's here. So this is alpha 3 of P3. On 4, I will do an edge flip. On 4, I will do, where's 4? There. What edge flip do I want to do? I want to do this edge flip. So this is alpha 4. So that means I need to take P4 down here. So this is alpha 4 of P4. And on P2, I will do a translation. So what translation am I going to do? I'm going to choose to do one that goes in along this ray. Okay, so this is alpha 2. And that means that P2, which was 1 away from V, now needs to be here. So this is now alpha 2 of P2. Translation of length 1. along that ray that I've drawn. Okay. This is a perfectly good homeomorphism of the Cantor space because I've taken a bunch of clopens to a bunch of clopens. And on what have I done on each clopen? I've done a restriction of an automorphism of this tree. So that means that what I've done is if I identify the root of this subtree with the root of this subtree, all I've done is move everyone around, possibly. Okay, so what I've done is move these subtrees, place them wherever I want, and inside do an automorphism of the rooted binary tree. Exercise, convince yourself that this H does not preserve the tree T. So H is not in aught T. This is a new element. And it should be easy because there's some adjacency that's broken somewhere, which I can't see because I'm too close to the board. But it's not difficult. Okay, so what is this thing? This thing has a name. This is F of aught T, and it's the we call it a piecewise full, but it's a topological full group for people who know about topological full groups. I'm not going to call it a topological full group because topological full groups are usually discrete, uncountable. And this is going to be a topological group in the sense that it has a topology that preserves the group operations. So I'm just going to say it's the full group. Piecewise or topological, however you want to call it, full group of aught T. Or it's also known as A aught T, so almost automorphisms of the tree. So it's a group of almost automorphisms of the tree, and it's also known as Neriton's group. Of almost automorphisms of T. Okay. Maybe, okay, I'm going to give you a proof idea of, I claim, right? I wrote fact. I said that this full group, is the commensurator of I. Okay, I'm not going to prove the equality. I'm going to prove one containment. Proof idea of this. Okay, so suppose I need to show, where is the thing about commensurating? It's up there. I need to show that if I take any almost automorphism, then the intersection of I with its conjugate by H is open in both. Right. Well, let's take this H that I've drawn conveniently. Right. Let's take that one. Let's see what does this do. I've run out of space. What does this do? What does this do on, so you can think of this picture as if I have my V, if I have my origin V here, then I've got 1, 4, 3, and 2 hanging off of there. Is it clear what I mean by this? So P1 is hanging off of here, P4 is hanging off of there, P3, and so on. And H takes it to, now let's see, where have they gone? So this is now 3. This is now H of 3, H of 4, H of 1, and H of 2. Okay, so I moved around all of the subtrees hanging from the leaves of this little subtree, and inside I've done some element of I. Right, so now let's see, okay, I'm going to do the following thing. I'm going to take the rigid stabilizer of the H I's. I goes from 1 to 4. Is it clear what I mean by that? The rigid stabilizers in this picture, inside I. And I'm going to see what happens if I essentially want to show that this thing without the H's contains something open. You will, okay, maybe you will see in a second. Right, what is this? Well, this is, oh, no, I want to do it the other way. Right, I want to do it this way. Okay, so this is a bunch of homeomorphisms of the Cantor space. Each of them acts on the Cantor space. So let's see what happens. Let's see what happens to a point that is maybe in partition 4. Well, first I have to do H to it. So I do H to it. It was in partition 4, and so now it's gone here. So that's here in the picture. Then I do something in the rigid stabilizer of this thing. So I'm just moving it around. And then I take it back with H. So it's gone back here, except that I've moved it around by something in the rooted tree automorphism group. And the same thing for all the other I's. So this is actually the direct product. This is actually the direct product. Well, okay, so this is actually the direct product of alpha I, rist I, H I, alpha I inverse. I goes from 1 to 4. And it's the direct product. I goes from 1 to 4 of rist I of the I's that I had before. Okay, so this says, so what does this say? So this says that that if I conjugate, so this is an open in I, right? This is an open in I. So this says that if I take I and I conjugate it by H, this contains H rist I of I's, I from 1 to 4, H inverse, right? Now I've put the H's the other way around, and this is exactly this thing, which is also open in H in this thing. So the intersection of these two, of the conjugate of I and I, contains this product of rigid stabilizers, which is open in I. This is open in I. And of course, this is the image of an open in I, so it's open in the conjugate of I. Okay, so H commensurates, at least for this H. And you can do it for arbitrary H. You just have to choose. I mean, this just depends on the partition that defines H. Do I want to? No, I want to leave it. I want to change the board. I have 2 minutes. Maybe I will take a couple more. What's so great about this? Well, what's great about this is that we have a theorem. Okay, we have many theorems, but I'm just going to give you one. I'm just going to give you one, and I'm essentially going to give you a reduced version. So if B is a compact branch group, so a profinite branch group, so one of these finitely constrained groups, I is a compact branch group, right? You can think of one of these finitely constrained groups, the closure of the Grigorchuk group, the closure of the Gupta-Sidky groups. Then the commensurator, the abstract commensurator of B, this we already know. This isn't our theorem. This is by Lavrenyuk and Nekrashevich, that it's the relative commensurator in homeo of the boundary of the tree of B. But the point is that I'm going to call this C, and C is the full group of is a full group. You can think of it as a full group of itself. This commensurator is a full group and is a TDLC group, right? Because what we've shown is that it's the commensurate, sorry, the other way around. It's the commensurator, so of course you can lift the topology up. The topology of B, you can lift it up to C. That is the whole point of commensurating, right? What's interesting is that the full group also commensurates. And this is the idea that I showed you. So the full group is contained inside the commensurate. And therefore you get this equality. Okay. Here's another result. Going back to the example, Kapudyan in the 90s showed that Neriton's group is simple. And compactly generated. Aha. So Neriton's group is another one of these groups in S. Right. So this commensurator thing is another one of these groups in S. And we are interested in the open subgroups of this. Right. I need one last definition and a theorem, and then I'll stop. Definition. So if G is acting by homeomorphisms on the Cantor space C, then the alternating full group of G, maybe I can do it. Well, no, I'll just write it out. It's all the homeos of C such that there exists a partition, open partition. There exists G1 up to Gn in G, and there exists sigma, it's not the set, it's generated by, and there exists a sigma in the alternating group on n elements such that H restricted to the ith part of the partition is Gi restricted to the ith part of the partition, and also H just permutes the parts of the partition according to an even permutation. Okay, that's what the alternating group is. It's generated by all of these things. By a theorem of Nekrashevich, if G acts minimally, then this thing is simple. So if we started out with something that's TDLC, then if G is TDLC, then the closure of AG will be a group in S, well, maybe if it's compactly generated. Okay, so the theorem that, so it follows from a theorem that Colin and I proved. So it follows from, I'll just write our names. Colin Reed and I proved something that implies that if B is one of these finitely constrained groups, for people that know what it means, it's enough to be a regular branch group. But since I haven't introduced that, just think one of these finitely constrained groups is a finitely constrained group. Then the abstract commensurator of B, which is again the relative commensurator inside homeo of D infinity of B, let me call that C, satisfies that C is full and is TDLC, and also that AC, the alternating full group of this commensurator, is an element of this class S. And moreover, I will just say it turns out that if you want to know, so if you have a group that's locally isomorphic to something in S, then basically, so it's open in something of this type. So the gist of the theorem, which I don't have time to write down, is that if you want to understand, oh, no, I said something. Okay, let me start again. Within the class S, there are different types. There are 5 types. This is a theorem by somebody else. One of the types is things that are essentially, one of the types is groups of this type, things that act on trees or almost act on trees. So for anything that is locally isomorphic to something of that type, if you're locally isomorphic to something of this type, then you're essentially one of these things, one of these alternating full group things. So basically, it's a theorem that says that in order to understand one of the 5 types of groups in S, it suffices to understand these alternating full groups. Thank you for the attention. Yeah. In a different way. Without doing successive commensurations, you mean? Or it's not the compact open topology from the homeomorphism group of the Cantor space, if that's what you're asking. Okay. No, it was actually okay. It wasn't defined as a commensurator, but it was defined like that. Partitions. It's the homeomorphisms. It really was defined as the full group of as yeah. 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 Then you show the way to give it a topology is by showing that it commensurates. So the thing is that I mean so it's not okay. So the way to give this a topology is by showing that this commensurates odd T and lifting that topology up. What's not so clear is that this is everything that commensurates odd T. I didn't tell you that. Second question. Well, the alternating group always, I mean, this thing is always simple by Nekrashevich's theorem. Well, or topologically simple. Yeah, when the action is minimal. But if you start out with something like a branch group, then the level transitivity tells you that it's minimal. Yeah. But the question is whether it's compactly generated. Yeah. Yeah. Yes, it's the same argument. It's expansivity. It's the same idea as in Nekrashevich's proof. I've hidden the expansivity in the fact that it's finitely constrained. It's shift invariant. And the fact that there's only finite, I mean, it's not just being shift invariant, it's the fact that you only have, it's this fact that the rigid state, okay, I'm not going to make myself clear, but it's the fact that the finitely constrained, the fact that it's defined by finitely many forbidden patterns is what gives you the expansivity. Mm-hmm. Yeah. It's, I mean, there's more that aren't just subshifts, but it's of a similar flavor. Yeah. You're welcome. Let's go have lunch. Thank you. Thank you.